Okay, so what is it heteroscedasticity that we have looked at so far? Let's take a brief review of what happens if there is heteroscedasticity. One is the coefficients are of course unbiased, but the formula for the variance of beta hat is wrong. Okay, it's no longer sigma square summation upon summation xi square. So we have two ways. One is to retransform the data by using weighted least squares, so that the errors are no longer heteroscedastic, right? And for which we developed the feasible generalized least squares, or to use either HC1, HC2 or HC3 develop the correct variance of beta hat. So the hypothesis test will have to be changed accordingly. The hypothesis test will have to be changed accordingly. Now we are looking at a related problem, the problem of autocorrelation. What is the problem of autocorrelation? The variance of the error terms is constant, but the error terms are correlated with each other. That is, here we are no longer going to assume that sigma 1 square, sigma 2 square are all different and the covariance terms are 0. We are going to say the covariance terms are non-zero and sigma 1 square, sigma 2 square, sigma 3 square are all constants. Right? Okay, that can happen if the residuals today depend upon the residuals in the past. For example, if you are trying to model, say, the sales of umbrellas as a function of the price of umbrellas, right? So on the y-axis you have the price of umbrellas, on the y-axis you have the sales of umbrellas in a particular month, on the x-axis you have the price of umbrellas in that month, right? Okay, and suppose you got monthly data for the last 5 years. Now, will this data have any seasonality? Yes, normally before the rain start, people buy umbrellas, right? You don't really buy umbrellas in winter. You buy umbrellas when just before it's going to rain. At least most people do that, right? And therefore, the data would be, so if this is the sales of umbrellas, okay, if here, sales of umbrellas in month T, right, and you have the price of umbrellas in month T, the broad relationship would be downward. Why? Because higher price would mean lower sales. But this relationship would be like this, right? If this is, so basically it would be like this. Let's draw this more carefully. So this would be a downward relationship like this, where if this is the trend, right, if this is the trend, every July the sales of umbrellas will be higher than what is predicted by this trend line, by this price line, by the regression line. Sure? Right, that is what seasonality does, which would mean that if this is the 7th residual, for example, and if this is the 19th residual, which will be 12 months later, if the 7th residual is positive, the 19th residual is positive, and so on. So the error terms will get correlated. The residuals will get correlated, and therefore, this is typically a time series kind of a problem. Okay, this is typically a time series kind of problem. The residuals will get correlated. What do you think will happen? What do you think will be the implications for the OLS estimators? First, will the OLS estimators continue to be unbiased? Yes, because for unbiasedness, what do you require? You require X and E to be uncorrelated. As long as X and E are uncorrelated, OLS estimators continue to be unbiased and consistent. So why should we bother about this autocorrelation? Somebody said that the T values will go wrong, right? Because the variance of beta hat, again, I'll quickly go over that, which I've done umpteen times again, right? Okay, fine. If yi, say yt, now so yt is the value of sales in time period t, xt is the price in time period t, and et is the error term in time period t. Okay, fine. Suppose now, so what's going to happen is, okay, we know that beta hat, okay, we know we know that beta hat is given by x dash x inverse x dash y, right? So we know that beta hat is summation xi yi by summation xi square, right? In this case, it will be xt yt by summation xt square, because we are now using t and not I, because this is time. So to indicate that, we are using, instead of the suffix I, we will be using the suffix t, right? So this would be summation xt which is what? Right? This will go, right? So we have our well-known formula. We have our well-known formula. Summation xt et upon summation xt square, right? Which is so, and as long as this expected value is 0, then expectation beta hat is equal to beta, right? So as long as x and e are uncorrelated, we have no problem, right? But what is the variance of beta hat then? Variance of beta hat beta hat minus beta square is expectation right? This all of you know, right? So again, thinking of a simple two observations case, this becomes equal to, so this becomes equal to x1 square even x1 square expectation x2 square x2 square expectation x2 square plus 2 x1 x2 expectation e1 e2 upon Now we are saying that this and this are the same, so we don't have to worry about that. So this becomes sigma square, this becomes sigma square, but the problem is this is non-zero, right? So if this is non-zero, the variance of beta hat is not sigma square upon summation xi square. So if you use sigma square upon summation xi square, your t values and hypothesis tests will go wrong. So the question then is, what does one do about this? So if there is autocorrelation, again the situation is identical to heteroscedasticity. That is, the estimators are unbiased and consistent, right? But the t values are no longer given, the formula for the variance is no longer given by sigma square upon summation xi square, but it's a different form, right? So let us try to understand how one models this by taking a very simple case, right? What is a simple case? Think of a model where I have yt, okay, is equal to beta xt plus et. Et is normally distributed and all that, but et is not independent of its past values. Suppose et depends upon the value immediately previous to it. For simplicity, suppose et depends upon et minus 1, right? So we write, so et is equal to phi et minus 1 plus vt, sure, where for simplicity we will assume